Okay, let us continue. The same example we had with this two-dimensional area, finding the tallest peak. Now I want to do the same, but I will now use the F-mean search instead of my own brilliantly designed walk just upwards algorithm. So F-mean search should be much more precise, much better. So let's try to run this one. So here we have the area, and then we drop them. Now I set the machine to halt, a pause between each and every one of them. Here, the small square, it's the starting point, and then the big white one, that's the peak that he found. What's important now, if you sort of pay attention, is the logic, how these algorithms have been designed, how they are programmed. Quite sophisticated. Sometimes he will start at one location, pretty close to a peak, but he doesn't find the closest peak. He finds another peak all the way over there. And then you move the initial point just a little bit, and then he finds a peak all the way over there. So the logic behind these routines, F-mean search and F-mean cons, quite complicated. So far, he has found the closest one. Let's see if we continue. That was very close. Close. Not so close. Close. Didn't find any. Didn't find any. Well, fairly close. Close. Sometimes now he will find some of the others, so you don't see it. So here with F-mean search, normally he will find the one that is fairly close to your initial point. Just continue with the rest of them here. Like that, and he found the tallest one. That's the same location that we had with my dummy algorithm, you might say. That was a F-mean search. If we now change to F-mean con, and now I have to specify if exit flag equals 1 or bigger, then it is okay. So let's run again. That was the first shot. I didn't find anything. Second, didn't find anything. Third. Fourth. This doesn't look too good. There we found one. That was very close. Close. Pretty far away. So, and the reason then to use random position instead of just an organized search pattern is just because of this logic with these routines, that they actually are so sophisticated that you can't really trust that he finds a local minima in the vicinity where you told him to search. He finds one all the way over there. So using random positions initially actually is a quite good idea. Now this one, he failed. He didn't find the tallest one. He found another peak somewhere else, not so tall. Not so stupid, of course, but still not so good. Now, it's not totally fair with this problem here using F-mean con, because it's actually not a condition. We don't have any constraints at all. Not that we have programmed. I just switched the name F-mean search to F-mean con. So that's sort of a waste of effort. So F-min-con really doesn't work well with this example. Okay, now for us, or actually for you guys, in any future problem, say you have a problem, a physical problem, you have used bond graph to solve it, you have an effort, you have an inertance, you have a spring, you have a resistance, you have whatever. Then you want this problem to act in a certain manner. You want to minimize a cost function. Then here it will depend on the value of these parameters into your problem. Or maybe this input function here, here is some effort 0 plus effort 1 times time plus effort 2 times time square, or whatever. You have constructed some given input function there with some parameters, effort 0, effort 1, effort 2. Then optimize this. You want the, say, position here, a velocity, and the position x should have a certain value. Okay, then you construct a cost function. And here I would say the input for this problem now will be E0, E1, E2, I, C, R. So here we have a 6-dimensional problem. And the cost, well, that will be one simulation of this system and then monitoring the desired value x, for instance. That could be a problem, a real problem for you. So find the set of parameters that gives a certain desired behavior. If it's a steady state solution, sort of you have some motion here. So this x as a function of time maybe have some behavior like this, and you want just a steady state. Okay, then it's fairly easy to play around finding a cost. The cost will then be the distance here if you want him to be as close as 0 as possible, for instance. And then you could play around with all these parameters, so this will happen, for instance. So my point is, any problem can be sort of continued to be an optimization problem. Choosing the right numbers so that you get a desired behavior for the entire system. No problem. The task then for you guys will now be that was the last year's, but never mind that. Here you have given an equation of a terrain. So like this two-dimensional geometrical problem that I've shown you already. So you have the z function, and here the distances, everything is given in kilometers. So 2 minus x1, 2 minus x2. Here x1 then should be, and x2 is given in kilometers. And the first problem, then the island is quadratic, the area is square. The second one is a little bit worse. That's a circle. So there you have to use some constraints, explaining to him that, okay, I want the position, the location for x1, x2 to be within the circle. There you need to do some programming. For the last one there, I think I had something here just to show. As an example of this island, giving a start and a stop. So he may or may not find the closest peak. So there you can play around for yourself. So when you do this, you can have the strangest walk pattern from the start to the peak that he finds. So the algorithm for this F-min-con is quite sophisticated. Of course, the correct solution you find very easy. You just plot them, and then you see, aha, this peak here has to be the biggest one. So you know the solution. But how to find it using this F-min-con? Not so easy. Not so easy. Here you have links to the documentation, so there you can find examples how this can be done. And also here in the doc for F-min search and F-min-con, you have all the way down here somewhere, you can look at the examples, how they have actually done this. So there you find the recipes, how to use these functions. The second task in exercise 5, that was the one that I just pointed out. You have been given here a quite simple system, and then we design a cost function. And here I've said I want the behavior of the mass to act like a cosine. So the x will not be a constant, the position. He should look like something like this for a given time period. That means we have to choose our parameter so that this will happen. And the cost function will then be the deviation from your real position in time. That may look something totally crazy, but he should then be as close as possible to a cosine wave. So that is the task. That's your cost function. So that you are given some hints here how to find this cost function. So, and also here you need to use an interpolation scheme. And here a cost function, the sum of the difference between your solution and a cosine wave. So every time you want to do this evaluation of a cost, you have to do one complete simulation. So of course this can be rather heavy if you have to do it many times. But this problem is just a two-dimensional problem. So what you actually can do, if you are worrying, have I found a correct solution or not? Well, then you can find different C's, different R's. You can plot this surface, and then you should be able to see for yourself. It's just a two-dimensional problem. Then you could see the solution directly, finding the tallest peak or the lowest peak within this area. So of course, if I had given you more than 2 parameters, like here you have 6, you have a very hard time plotting it, of course. But for this example, it should be possible to find it. Okay, any questions to optimization? That's okay. Then actually I hadn't any plan to bother you with anything else today. No, it's too boring. So if it's not any questions from the room, no? It's way too late anyway. Then we stop a little early today.